We're back. My mistake. Hey, Phil. Welcome. Welcome back, everyone. I would say thanks for joining us today. Please do pop along to the Slack. So bit.ly/ATTO-Slack to join in the conversation. Please also feel free to donate to the COVID-19 Solidarity Response Fund. We're raising some fantastic money for that. So please do pop along to the website, learn more about donating. I won't take up too much of your time there, Phil, because it's a short session, but the title sounds superb. Yeah, Kubernetes Un-Scaried, which I think we could all benefit from. So without further ado, let me add your screen in there. I shall disappear and over to you.
All right. Thank you very much. Thanks to All Talks for having me. I've never done this virtually before, so this is going to be interesting. Hope you'll bear with me. I hope you can all see my presentation. If not, somebody will have to poke me. To begin with, a little bit about myself. My name is Phil Taprogge. I am the SRE lead at Sneak. I'm also resident nerd and a certified Kubernetes fanboy. I've been into sort of infrastructure and cloud computing jobs, platform engineering jobs for the past 5-6 years. And I genuinely believe Kubernetes is one of the most profoundly game-changing technologies that has come about in the past decade. So let's talk about Kubernetes. There's a lot to talk about. Strap in and bear with me. I'd like to begin with asking and then answering my own question: what actually is Kubernetes? And, it's a question a lot of people kind of sort of know. And if you look at the sort of blog posts on the internet and whatnot, you'll find many high-level explanations, and they all boil down to pretty much one thing, and that is it's a container orchestrator. So what's that mean? Well, it runs our containers for us. To which I then usually ask, so what does Docker do? So obviously, there's more to it than that. Daniel Rieck from Red Hat once famously said, OpenShift, Red Hat's Kubernetes distribution, is the new enterprise Linux. And it's a big statement, right? Kelsey Hightower once famously tweeted, Kubernetes is not the kernel, it's systemd. And I think Kelsey actually was spot on with that remark, because at the core, Kubernetes is just a bunch of state machines, just like systemd. What's a state machine? Well, it's a mathematical model that helps us understand compute. It's a system that has states, and it has rules for transitioning from one state to another. In Kubernetes, there are control loops. They have states, and those states are represented by the API objects, your deployments, your pods. And they have rules for changing from one state to another that are driven by changes to these API objects. A Kubernetes control loop looks at state in the API server. When that state changes, it does one of two things, or both. It either interacts with an external system like a cloud provider or the Docker daemon, or it writes a change to the API itself. So let's look at an example for that. And just a word of warning, I did try and find a better diagram that visualizes this. Unfortunately, I couldn't find one that wasn't copyrighted. So I had to make my own, and you'll quickly see that they don't pay me for my graphics design skills, but bear with me. So what happens when you create a deployment, say? A deployment in Kubernetes, you'll probably know this, is a high-level object that expresses a desire to run a number of containers somewhere on the cluster. So how do we get from the deployment to a container? You create a deployment either through kubectl apply or through a client SDK, or even just a curl with a post. And the API server will receive your deployment, and it will write that to etcd, persist it, and that's all it does. The API server doesn't actually do anything. It gives us authentication, authorization, it gives us validation, but it doesn't do anything as such. For that, you need controllers. And most Kubernetes controllers are bundled up in a thing called Controller Manager, but they're all independent pieces of code, each one doing just one thing. In our case, there is a thing called the Deployments Controller. And the deployments controller is interested in changes to deployment objects. So the deployments controller will find out that there is a new deployment that was just created. And that could have happened a second ago. It could have happened 5 hours ago. It doesn't care. It always does the same thing. It knows for a deployment, there should be a replica set that matches that deployment. It will check, is there one? In this case, there isn't, so it'll create one. It'll write a new API object. It'll copy some of the details from the deployment, like the pod spec, the replica count, and write that into a replica set object, persist that through the API, and then it goes back to sleep. There's no containers. There is, however, a replica set controller that now wakes up, having been informed that there is a new replica set, and it does a very similar thing. It knows for every replica set, there should be a number of pod objects indicated by the replica count. It checks, are there these pod objects? And if there aren't, it will write some to the Kubernetes API. But pods aren't containers. Pods, again, are just a desire. They express a desire to run a container somewhere on the cluster. So we need to find the compute resources to run those containers. And that's where the scheduler comes in. The scheduler has a bit more of a specialized taste. It looks for specifically pod objects that are in state pending and that do not have a value in their node field. When it finds those, it looks at the nodes available on the cluster. It picks, whichever way it does, a node that is best suited to run that particular container. It looks at things like node selectors, it looks at resource requests, it looks at what the nodes have to offer, and it will then pick a node. It will write that node's name into the node field of the pod, and it'll go back to sleep. Now, I hear you crying, what sort of scheduler is this that doesn't actually schedule anything? But in fact, it does, because by doing so, it gives kubelet, which, as you'll probably know, is the node agent that runs on every node in the cluster, enough information to realize that this pending pod with its name on it is something that this particular kubelet should be responsible for. And kubelet has another control loop that says for every pod with my name on, there should be a Docker container on this machine. There isn't one currently, so it will construct the Docker run command that will make that container appear. It'll update the status of the pod, indicating that that is now running, and now finally we get to a point where we've actually got the container that we're looking for. So why is this sort of convoluted process so powerful? It's because every one of these components, by being so independent, is by design and by default self-correcting. Everything will eventually fall into place when the stars align, as it were. There were no timing or orderliness guarantees to begin with, so all of these control loops have to look at the world afresh every time they run. And when something goes wrong, once that problem is resolved, everything will come back together. There's no need to restart anything. These control loops don't carry state, so they can fail and can come back and just pick up where they left off. And they don't talk to each other. They only ever communicate by way of changing state in the API. You know, looking at the previous example, what happens when the scheduler wakes up and there are no nodes available for your container? They're all busy. Well, it will mark that pod as unschedulable, and then it goes back to sleep. It requeues it, basically saying, I'll get back to you. And from that point on, it will retry for days and even weeks if it has to, knowing that eventually there will be compute power again, and when that happens, it'll run the container and everything will come back together. Why am I telling you all this? Mainly because there's actually two reasons. The first one is because it makes Kubernetes incredibly extensible. Each one of these control loops is independent. It does one thing. You can rely on it. And you can add control loops into this mix that will all play nice with whatever's already there. In other complex systems, if you want to make a change and have it work, you have to understand a lot of how everything plays together, how the communication paths work. If you've ever tried to contribute, say, to the Linux kernel, that's a lot of work. With Kubernetes, all you need to know is how you need to manipulate state in order to get the result you want. That's the only way communication ever happens. And the second reason is because you have to do monitoring differently than you used to in a system that consists of discrete hardware. Something goes down, you want to know about it so that you can go and fix it. On Kubernetes, you really want to have at least two of everything. And Kubernetes makes that easy. And once you have two of everything and you have a system that is self-healing, you no longer want to alert on the thing is broken, but rather the thing has been broken for longer than you would expect. And trust that in the meantime, the other one of the two that you should have will take over, and you ideally don't have any customer-facing impact as the system realigns itself and things come back together, fall back into place. This extensibility is important because Kubernetes, like many things that came out of Google, strictly follows an 80-20 rule. It does a lot of things for a lot of people, but not everything will always work for everyone just as it is. Also, there's a couple of areas where they kind of forgot a few things that aren't really very well covered, and we'll look at a couple of those in a minute. But because of the way it is built, it is actually quite easy for anyone to add custom controllers into the mix, and with relatively little investment, you can unlock a lot of potential. If you're interested, or after this talk will be interested in doing something like this, I recommend you have a look at KubeBuilder, which provides you with a framework on how to build custom controllers for Kubernetes with a lot of scaffolding that makes it even easier. But to look at an example of this, I'd like to point at managing configuration. You will probably know that pods can consume config maps and secrets, either as environment variables or as mounted volumes. And that's great. We love separating code and config. But what happens when the configuration changes? Well, if it's consumed as environment variables, we're kind of screwed. The environment for a process can't really change after the fact, so the container would need to restart to pick up those changes. But Kubelet doesn't know that that restart is necessary. And even if you're consuming the configuration as files, which will eventually change on the container file system to manifest that change, it is now your process's responsibility to monitor those files and reload on change. Some processes can do that, some processes can't, so the results are very inconsistent. And in my previous job, this bit us a few times early on, and after a couple of incidents, I decided that enough was enough. And I figured, what's a platform engineer to do? Well, you write a custom controller. And that's where Wave came from. And Wave is a surprisingly simple piece of code that really only does one thing. It looks at all the config maps and all the secrets that a deployment pod spec reference, and it then calculates a hash over their contents. It stores that hash with the pod spec in the deployment, and then it watches for changes. If someone now changes a config map, it will update that hash and write that updated hash into the deployment's pod spec. And because the pod spec has now changed, we get the same effect that as when anything else in the deployment changes. Say you change the command line of the container or the container image, it will trigger a rollout. So the deployment controller will kick in, it'll make a new replica set, the replica set will make new pods, and it will honor all of your min available and max surge. And that we didn't need to reinvent that wheel at all. The only thing that Wave does is it triggers that well-known, well-understood process by making a change to the deployment. Another of these gaps is secrets management. Kubernetes secrets aren't really very, very secret. They're great for consuming in cluster because they're just base64 encoded plain text, but they're not very great for storing or managing outside. And there are a number of solutions for this, but all of the good ones follow the same pattern. They give you a custom resource that is a proxy to your secret, that is safe to store, safe to handle, but contains enough information for a controller on the cluster to recreate the actual secrets object on the cluster itself and keep them in sync. One example is Bitnami's sealed secrets controller, which uses asymmetric cryptography with a key held on the cluster that allows the cluster to decrypt an otherwise encrypted sealed secrets object that you can store in Git. And that is safe because only the cluster itself has the key to decrypt it. Another one is the external Kubernetes external secrets, which can keep a secrets object in sync with, for example, information stored in AWS Secrets Manager. But in both cases, you have an object that is kept in sync with another object, and that's done by a controller. Speaking of cluster state, I said storing in Git, that in fact is one of the big challenges you have when you want to run Kubernetes in a large deployment in production. How do you manage that desired state when everything is changing all the time and so many hands are involved? And the best practice that is emerging on that is using Git, a practice called GitOps, where your operations are triggered by changes to Git. So you have a Git repository that is already versioned. You put your, for example, your raw YAML objects into that repository, and you use a controller to continuously keep the cluster in sync with what's in that repository. One example that does this is Argo CD, and I would strongly encourage you to take a look at that approach if you plan to run Kubernetes in a largish production capacity. Another thing you'll have to look at is obviously monitoring and alerting. There's a lot of moving parts, a lot more than systems of old used to have, and there's a lot more data that you need to understand what really is going on. You don't want to just deploy Prometheus and Grafana and call it a day. Spend some time actually building good dashboards that tell you a story. I promise you, future on-call you will be very grateful for those. And you want to build your alerts around persistent errors, not spikes, not short changes that should really be correcting themselves. Ideally, you want to look at leading indicators, things like increasing latencies, increasing requests per second, these sorts of things, so that ideally you can take action before something breaks. A lot of this stuff can be automated. For example, horizontal pod autoscalers allow you to scale out your compute capacity as your load increases. But where those systems fail, you want to be alerted of those trends. And lastly, of course, you want to make use of your error budgets. Nothing is ever 100% up, and understanding how much down is acceptable to you allows you to build alerts that only really fire when it's necessary and don't distract you and leave you time to work on things that are more important. Lastly, I did promise in the blurb an answer to the question, should you roll your own cluster? And I guess I should probably come through with that. The answer is, it is complicated, but I will say nothing that I've described so far requires you to self-host. All of the stuff that I've talked about, writing custom controllers, doing your alerting based on their metrics, all of that can be done in GKE, can be done on EKS, it can be done on OpenShift, any sort of Kubernetes will do. But do remember the 80-20 rule. Basically, if your payloads are reasonably similar to what about 80% of everybody else is doing, you're probably going to be just fine with GKE, EKS, what have you. And if you're doing something particularly unusual, you'll have to do some extra work anyways to make Kubernetes work for you, and you'll need good engineers for that. And if you have those, self-hosting Kubernetes isn't actually all that difficult. We used to do it. We had 4 or 5 production clusters. We managed those with a team of 3 engineers, and we had maybe 1 on-call paged event a month, thereabouts. So that can be done, but really it comes down to what your payloads look like. One example, when we started using Kubernetes, that was like 1.5 times. We didn't even have ingresses yet. And at that point, we discovered a problem, I would argue a bug, in the way that container resource limits were implemented that led to, in the worst case, an almost 100 millisecond delay being added on every hop of a request through a network of microservices. You can imagine if you've got to go through 10 plus microservices in order to service a customer request, and in the worst case, you add 100 milliseconds at each hop, that quickly adds up. So for us at the time, we were doing real-time communication APIs that wasn't really acceptable. And so we ended up actually running a fork of Kubernetes for a couple of versions until a fix for that got integrated into the mainline code base. And we could only do that because we controlled the control plane, the API server, the controller manager, kubelet. If we had been on something like GKE, we wouldn't have had a prayer. So we made that decision because we knew real-time stuff was fairly new and Kubernetes was fairly new and not many people were doing it. It turned out to be the right decision, but really that's the question you should be asking yourselves. Am I doing something unusual? Am I doing something new? Or am I just doing what everybody else is doing? In which case, hosted will serve you just fine. And with that, I hope there should be some time for questions. I did not look at the time. Maybe.
Perfect, Phil. Perfect. Yeah, thanks very much for that. That was really good. And yeah, we got like 7-8 minutes luxury amount of time for questions. Yeah.
Okay.
So I've got a couple racked up. The first one is from Chris Kotzman, said, Phil, you mentioned monitoring, investing time in building good dashboards. Are there any existing Grafana dashboards for Kubernetes based on best practices?
I'm sure there are. I'm afraid I don't really know many because, as I said, when we started using Kubernetes back in my previous company, that was fairly early on. So we built our own set of dashboards, and so I never really had a need to look elsewhere. It is always a good idea, though, to have a look around. These sorts of challenges are not unique to you. Running Kubernetes is something that's becoming more and more popular. So more and more people are looking into solutions to common problems. Dashboards are one of them. Yep. I know there are resources out there. Unfortunately, I can't point you to one right now.
No worries. I'll just quickly chuck in. I know the Prometheus folks have got some really good stuff. The Grafana website itself has got a bunch of cool things. And some of my friends are talking, if you're running service mesh like Istio, Kiali is well worth looking at.
Oh, that is actually, yeah. Yes, we did run Kiali. Kiali is great because it visualizes the flow through your service mesh in a way that makes it a lot easier to pinpoint where problems are.
Yeah, I found that very useful. Well, the other question here is, you mentioned a lot of cool stuff there. If someone is investigating Kubernetes, where should they start?
Investigating as in you want to play around with it?
Or looking to run sort of in production, I guess, is the state.
Well, I think if you're new to Kubernetes, running Kubernetes yourself to begin with is always a good idea. GKE makes it incredibly easy. Just spin up a cluster, and within minutes you can run your kube control and you can try out whatever it is you want to try out. If you want to run Kubernetes in production, really that's where I would start, and then add to that all the things that make it production ready: monitoring, alerting, looking at what sort of workloads are you going to be running. You'll want to think about what sizes and shapes of nodes your cluster will need. But it is, because everything is so componentized, it's a system that is very easily sort of built out of building blocks. You can start simple, and as your needs evolve, you add bits to your cluster.
Super, Phil. Another question from Tim Nicholas. Can you give some other examples of what now might be non-standard or off the beaten path when it comes to running workloads on Kubernetes? Where is the edge of normal now?
I would say the edge of normal is moving very, very quickly. So it's as Kubernetes becomes more mainstream and more companies look at moving their existing payloads to Kubernetes, they are investing and thankfully sharing a lot of effort in how to make that happen. When we started, really the only thing that worked well was something like your e-commerce applications, a web shop or something. trying to do real time on Kubernetes was very unusual. That's changed now. I think that the niche where you're really doing something new is becoming smaller and smaller. I would say one thing certainly that is not very commonly done is running things like databases of large scale databases in cluster, and that's because cloud providers make it incredibly easy to just buy in your RDS or your Cloud SQL database as a service and sit that next to your Kubernetes cluster. If you're running on bare metal or for some other reason you can't or don't want to use that, that's an area where you may want to invest some time and engineering effort to build good solutions that allow you to run those payloads in the same sort of automated self-healing way as everything else.
Super. Time for one more question, Phil. If I was going to run Kubernetes locally, what's your favorite tool or recommended way of doing this?
Oh, so what is it called? Kind is what I would begin with. Kind is relatively new. People used to use Minikube a lot, but Minikube fiddles a lot with VMs and is sort of very heavyweight and can be more effort than it's worth sometimes. Kind instead tries to build a Kubernetes cluster out of Docker containers. So each node becomes a Docker container running Docker in Docker. And as long as your machine has enough resources, it's fairly quickly to spin up. It works pretty much instantly, and it's very good for experimenting. We use Kind for like end-to-end and integration tests of Kubernetes payloads. And certainly I think that's where I would start if you don't want to go to a cloud provider and spin up a hosted cluster there.
Super. Thanks, Phil. Well, really appreciate your time. Fantastic presentation. Please join me in thanking Phil on the Slack. We'll see you on the Slack, Phil. There's more questions there if that's okay with you.
Absolutely. Thank you very much.
Thanks again for your time.